Okay, so what we are going to do today is that today we will start. So from today we will start to prepare demo with every single board, and so like basically I just want to go through each board and fix whatever is missing there. And one important thing that many boards they don't have connection to sound generation using using I2S. So uh, let me actually connect to different computer, and then I will show you all the components I have, and then we will get a board and we'll connect I2S to that board. Okay, just a moment. Let's give me like three minutes.
Maxim, I have sent the invitation.
All right, thanks.
Вообще народ не хочет просыпаться в 11. Я уже понял. 2 часа еще кто-то приходит, то выделся. Second. Окей. 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 Так. Я не понял. Она что, включила еще одну камеру? Нет, это та же самая камера. Все. Все, хорошо. Okay, so first of all, I want to show the board I want to use as a main board today. So this board is on AliExpress. Yeah, so let me share my screen. One second, let me add multiple participants can share. Just a second. Okay. Okay. Okay, this is literal Terra board, which like has a lot of buttons and 7 segment, but it doesn't have a microphone, and it has its sound. But I'm going to add like external I2S connection. So let me get that one. Yeah, basics graphic music. So if you look to the board wrapper, this board is called EMOOCCC. So this is a website with this board. So if you look inside the wrapper, or actually let me get a let me show it in a GitHub. Mhm. Okay. So if you look to this board wrapper, this board was actually implemented by Alexander Mikhailov, Shuik. So you can actually discuss this board. Oh, 1 second. I need to put a speaker to put like sound everywhere. Okay, Shuik, maybe you can describe this board while I'm looking for this.
Hello, I'm Alex. So,
Can you just start from the start? I will give you the board and you can
yeah, we
describe
need to
what
look
this
at the board
is
very
and
first.
how it works.
How it looks, it's very, relevant to how you program it. The board has bunch of buttons, bunch of switches, bunch of LEDs, 7-segment indicators, and the code basically make use of that. Rather, I should say straightforwardly.
So can you describe what happened once we run an example briefly and then explain everything inside the wrapper? So like in order to implement a new board, we have to use.
Yeah, we need to show it
So
to
yeah,
the
you can show it
to the camera.
So now you need to tell that in order to connect it to a graphical display, we have those 3 options. Okay. So now we have this this HDMI connector, which is PMOD DVI. We have VGA connector. We have another VGA connector. And now, so you can continue. Yeah, just to describe everything this way. Yeah, you can show the code, so everybody saw the code. So you can just describe everything in this wrapper. Then we start working.
So there is a wrapper which uses some predefined names, some predefined logic to call those things, to incorporate those modules into kind of big system and then use that. So we describe signals which are used. We say how many of them are there on the board. We know that, for example, on the board we have 8 switches and 8 buttons and 8 LEDs, and all of that should be here. Is it that file? Yuri, is it this file for this board? emove.
mooc.cc. Yes, this is
This board.
mooc.cc.
Okay.
emooc.cc. So just like describe everything you have here. Let's connect some.
Yeah. Okay. So according to description of the board, we have 2 UART lines here. I don't know if we have like 2 UARTs, but we have like 2 UARTs lines here. We need to open that manual for the board for that, I guess. We had it somewhere. We have plenty of GPIOs. This one was added early on. We figured out that we need to have a button explicitly for resetting board without like repowering it. So that's why we have a concept of like top switch and reset line here. W digit. Yeah, we have 6 digits because we have 6 7-segment indicators, right? We have those digits. Well, actually, yeah, coming back, we see that here we have all those important resources enumerated here. Why we have 16 LEDs? Because we have 8 here and 8 there, right? 6 digits, and we have 3 banks of GPIO. Why it's like this? And one bank is probably includes two other banks. No, it's not like that. I need to look into manual. I don't remember what's there. The board description. Yuri, do you know where the manual is for this board?
Yeah, so go to a website called, go to a website called, no,
Okay,
get a
new
new
one.
tab, yeah, emooc.cc.
Okay.
Okay, now scroll down, yeah, here, no,
It's this one?
yeah, this one, yeah. So one of goals for today is to make a nice demo using this board with all the like different microphones and speaker and with VGA and so on.
Let's find the manual. Should be PDF file somewhere.
Yeah, they have everything, but you just need to scroll and find
Right.
everything. I think you already scrolled too much. Just a second. Let me
Okay.
find it for you. Okay, light.
Just a picture.
Yes, actually, I think I have a documentation in GitHub for this board.
Yeah.
So let's see what we have here. Yes, I got pins from a manual. I don't remember already where I got the manual, but this is somewhere on that website. And this is a QSF file with all the pins connected to ports with symbolic names.
This is what we're looking at.
Let's see what we have here. So here we have a microphone, but we don't have. Here we have a microphone, but we don't have a connection with anything that produces sound. And for sound, we have multiple options. So let me show. But first, I want you to just explain what it has already and explain how microphone works. Just like explain what you did to add support for a new board.
So yeah, I mean, this one's done later on. The first thing was probably at the top. So we wanted to make sure that like buttons respond, that LED could be lit. I think the initial labs they test exactly that. It's like yeah, those are comments mostly for myself. I was trying to understand what was going on. This is, I believe, especially this symbol is because assumptions on the board is different than assumptions in the like the opposite assumption in the code for the lessons. A, B, C, D, F, G. What we had here. This is the part which is related to generation of VGA signal. Of course, we need to have like two signals, two pins on GPIO reserved for VSync and HSync, 3 pins for red, green, blue. And later on, here we assigning them. And then we assign red, green, blue. Only it's not single pin. It's like 4 pins for each of them. And then later on, using that VGA connector, VGA adapter, it gets converted to one of 16 levels of the signal.
Yes, wait,
So,
so before you talk about details of your
right.
wrapper, you need to define what is the main idea. The main idea is that we want to make top module, which is a top module instantiated here, which is completely abstracted from a specific board and tool chain.
The
So
top
that's why
module,
the purpose of this module is to connect board specific pins to board independent things.
those parameters are all different for different boards. Here we're sort of explaining that we have keys and there are like 8 of them. We have switches and there are 8 of them. We have LEDs, like,
And then like eventually we
but we
instantiate
don't
those
have
modules.
something else. We don't have, like, for example, digits are only 6, not 8 as on some boards, and not 4 as on some other boards, and not 0. I mean, we have these numbers of GPIO. So yeah, some other possible resources could be on other boards. So the so this is board. This basically is its file which describes the board itself. The wrapper, the code which uses this file, can check those parameters and knows like what can be done, what can be callable, what resources can be used. We do not currently include buzzer and EEPROM. I think we have something on the board which we just don't use right now, but I just don't remember. Again, we need to look into this PDF file. We had PDF file taken somewhere from here and translated that automatically to English. And it was mildly useful. It had some lists of signals, but need to find that file again. Yeah, some files were extracted. I mean,
it doesn't matter because
yeah,
it doesn't have anything interesting. So like practically
maybe
we just got pins connected cyclone for FPGA to like external peripherals, which is just a GPIO and something trivial like the 7-segment a display. Okay,
over here.
second, let me give you.
Yeah, I was looking for that.
It doesn't.
Sure.
This like PDF doesn't have any useful information whatsoever. All useful information is in this text file. Hey. Okay, just to sit down. So today we are just slowly working through specific boards. So now we are going to connect like a microphone and so there are like several components we are going to connect. By the way, you can connect it to that board as well, because this is not connected. So we are not doing like anything like particularly interesting, just doing details with some boards. It's up to you. You can sit there. You just move things. Huh? Yeah. So yeah, let's move. So what are you trying to do?
Trying to figure out what needs to be explained, like, and how.
Okay, so basically one thing we have in our labs. In our labs, we have a microphone and sound recognition, and the exercise we generate sound.
And all of that works independently of the board. So the specific board needs to be attached to that generic code, and we need to have lots of mappings. That's main the idea of this board-specific top file.
And not only board specific, we have also different microphones. In order to like abstract microphone, we create a set of microphone modules. So this one specifically, this one uses this microphone. So you can like demonstrate. So we need to connect this microphone to this board. And after this, we need to put module which connects one of these components to this board. Okay.
I don't remember what those names for the microphone signals are. There are 6 of them in this specific microphone. We connected them to pins and specified which pins they are connected to. Yeah, here is the hint, I2S protocol. So those signals are like I2S specific. Clock, data, I believe. These two are not. I don't know what they are. Maybe this will help. Yeah, we don't have that original PDF. Yeah. Maybe we can translate it somehow. Nope, doesn't really work. Okay.
Okay, sure. So let me talk about those components and then just start working with the board because some people finally came, and so we can start working with the boards. So today is like a boring day. We just are trying to make people work with like several boards. So first of all, let me show you components I want to add to this board. So there is this component which is called a pmod mp3, which is a component that produces sound. Now you can find this component on a Digilent website. Just a second, let me check. Meeting. Okay, so let me get a Digilent website and I will show you this component. So we were using this component in the School of Digital Synthesis. So it's a Digilent pmod mp. So you can see this component on the screen. So this component uses protocol called I2S. So here it is saying I2C, but actually this is I2S, and like this component can be used to generate sound, but the main problem with this component is that it is too loud. So if you are trying to use some earbuds, so let me show earbuds. So if you are getting like a headset or if you're using just a standard earbuds, in this case it produces very loud sound, and many students who were using earbuds, they actually complain about too like a high volume, so we stopped using it. However, there are several other components on the market, specifically like this component and this component and another component, and they actually different, so they produce sound which doesn't damage ear, and like I want to add those components to all the supported boards to make it a standard for the like next year of School of Digital Synthesis, and to use it in various other seminars. So let me show you how those components look like. So this is one of them. Let me tell a little bit what is like special about those components and how they differ from each other, because yesterday I tried all of them and they are slightly different. So here is another component. Op 5102 I2S. I2 I2S. Okay, so here is one type of component, and yes, and here is like another variant. Okay, and I had another one. Just a second. So this is sound card. I think I ordered it using Amazon. Anyway, they all use the same I2S protocol. So this is the same. So this is the same. This is the same protocol as microphone protocol, but with somewhat different parameters. So I will describe this protocol in just a moment. Yeah, so they're using a chip called PCM5102, and such two boards are used like frequently with like a Raspberry Pi, so they produce good quality of sound, and it is not too loud. However, as you can see, it has like many pins additional to pins of a regular I2S protocol. So, like in a regular I2S protocol, we have like voltage, ground, and we have um, like data in select, and then we have this block, this B clock, but also you can see some signals like format, XMT, DMP, FLT, and those are control signals which have to be set to like either 1 or 0, because they represent different options for this chip. So first of all, let's look to the basic module driver for this protocol. So if you Google Y2S, you can get some detail about this protocol in Wikipedia. So you can see here that this is a very simple protocol. We have some serial clock, and we are doing word select, and then we send data for left channel and right channel. So we send serial data bit by bit. And now if you look to the module which implements this protocol, and this module is available in labs common. So you can go to labs common, and this module is here, I2S audio out. So you can see that in this module we have clock, we have reset, we have input data, and this input data and this input data has a resolution of 16-bit, and it has like it has output for the M clock and B clock and selector and the data. So this is a very simple module, and basically what we do in this module, first we need to divide clock, and because this clock does not go into clock tree inside FPGA, and this is like external clock which just goes outside to send something. We don't need to put this clock through special modules like we are doing with divided clock in our other examples. And all we have to do is that we have a shift register, and we essentially put this 1-bit data by shifting a value we are getting from input port. So this is essentially a shift register. So now, what is the difference between two different like between the four different chip? The main difference is how we treat control signals. So if we are getting, for example, this chip, we have to connect not only header, but we also have to put soldering bridge. So we have to put a little bit of solder to a specific place on this chip. So let me find this picture on the web. So soldering bridge 5102. Yeah, so we have an article like how to make PCM 5102 digital to analog of converter work on Raspberry Pi. So here is this board, and just let me show you soldering bridge. It's not here. Yeah. So you can see that here, when you receive this component, you have to add a header here, and if you don't want to use any control pins, so you can see control pins on the top, which is L, R, O, U, T, and so on and so on. You need to put just a little bit of solder to this connection. So you need to put like solder to solder to make a low for H2L, H1L, H4L, and high for H3L. And by doing this, you are setting some control pins, and there is a document in internet which actually explain. Here is a document which actually explain what those control pins are. But if you put soldering bridge on this component, you don't need to set those pins. So there is a pin called filter select, normal latency or low latency, and de-emphasizing control for sampling rate. Then there is a mute, and we should not put this mute, and audio format selection. So we simply need to set it to proper values, and on this component we are setting it to proper values just by putting solder here. So this is one component. So then there are two other components. One component with the same chip, which is 5102, but with these components you don't have soldering bridges, so you presumably need to connect control pin like either to ground or to voltage. And there is another component which uses different chip, and this component is called I think I found it on Adafruit. So let's see. It's called Adafruit I2S. So let's Google for it. Yeah. So if you go to Adafruit, you can see I2S breakout, and there are many sound components, similar sound components. So let's find this particular component I'm talking about. Just, no, this is not a microphone. This is I2S. Okay, so this is a microphone. Uh, let's see. I think it's called I2S. I2S breakout. Just a moment. I find this another board. I think I put it in on Amazon. It should be in my orders on Amazon. DAC. What does it sound? It's yours. Yeah. Okay. So this is called 1334 DAC module. Yeah. So this module uses different chip, but this module also has a similar pins. So it has control pins, and this module actually allow you to connect your sound output not just to earbuds, but also to like large speakers. So if you want, you can amplify sound and do other things. So let's find information about this component. And today I want to connect those components to various boards we have. Yeah, so here is overview of this component on Adafruit, and you can see it's like a perfect match for any I2S output audio interface, and it can use like different voltage level and has like multiple different options. So now the goal of today is to connect those components to several boards and to create a demo of this component. So one is Altera board we just discussed, and another is a Govin board. So like another goal for today is connect this and create a demo on a Govin board. So let me get a Govin board and demonstrate it. Okay, so this is a board called Tank Primer 20K Lite, and this is an expensive board which we can buy on AliExpress. So we will connect this sound output to this board as well if it's not connected. So let's go back to our repository. So tank primer 20K light. And in addition to connecting this component, we also need to change pin assignment for microphone and for like other parts, specifically for TM1638, because I don't like the fact that it's connected to pmod. So we will create an alternative version of this wrapper and probably obfuscate this wrapper. So this has TM1638 and this has microphone, but this doesn't have sound output. So by the end of today, we should have a complete demo of at least Altera board with a microphone and with sound output. And we also need to have a complete demo for this Govin board. So let me show a demo what this board can do right now. Like what this Govin board can do right now. So let me connect this Govin board to this computer and run some example. So for example, let me use a terminal. Wait. Yeah, so let me use a terminal and let's go to labs. Let's go to, like, let's say hex counter. And just choose another FPGA board. So we need to run a script. Choose another FPGA board. And here we need to choose board Govin 10 nano. This one should be closed. Let's close this terminal, kill terminal, kill terminal. Yeah, this is board number 49, which is tank primer 20K light. So now we are running synthesis script for this board, which for Govin runs very fast. Okay, so you can see that this is the result on this Govin board that now, like, it's running a counter. So now we are going to connect this sound output for all the boards and to make sure that we have demo on multiple boards. Okay, now I probably work with like every participant in the room. Huh? What? Oh, I think it uses JTAG to configure design inside this board, but I'm not sure about the details. It uses a program called OpenFPGA Loader. Yeah. It's loading bitstream into FPGA. Yeah. So now, I demonstrated those components, and now I will probably work like individually with people in a room to make this a common demo. So I'm not sure how much I'm going to describe everything, but a kind of idea is to make this component standard. Let me actually show demo with another Altera board and this component. So I have another Altera board which is called A-Links, and this board just happened to be in Azerbaijan, where I was traveling back in February, and just like many other places, they bought those boards like several years ago, and they were not using those boards because they were not able to, because they bought those boards without USB blaster. So they cannot even configure those boards, but I brought to them USB blasters, and they were able to set up their curriculum on FPGA. And just in the same way, like many universities are buying different boards, and they're just sitting in their closets, but by using this set of examples, they can actually use those old boards. So now let me connect the sound output. Yeah, so to this sound output I connected one of these devices. So now we can connect earbug and listen to the earbug, and we have like several we have two examples. One is playing some music. So this example is called 24 I2S music, and another is 23 I2S synthesizer. So we are going to 23 synthesizer, and then we choose another FPGA board, and this FPGA board is called A-Links AX4010. Okay, so now we synthesize for this board. So generally, in our set of examples, we encourage students to use scripts rather than to use GUI. But some students who want to use GUI, they can use GUI, like Quartus GUI or Govin GUI or Xilinx GUI. So let me just show how it works, and then we'll start doing such demos. Hi, yes, another person just joined us. So basically, today we are not doing anything like interesting. So what we are doing is that we have like some specific boards, like this Altera board and this Govin board, and we are adding to them 4 different I2S components. So we'll try with each boards like different type of components that use I2S interface, and the goal is to make a demo for this interface. So okay, let's hear this. Oh, but it's yeah, it's a very quiet. Yeah, so this is like electric organ, so you can actually listen to it. Oh wait, I had to put speaker. I didn't put speaker. So can everybody hear? So now we can like press different buttons and play like different tones. So C, C sharp, D, then D sharp, then E, E sharp. So we can play like various music notes. And another demo we have is a demo called 24. Yeah, those demos, they were created by a student, former student Viktor Prutyanov, who was studying in Moscow Institute of Physics and Technology. Then he created set of examples in that place, and then he contributed to our examples, and then he was in Skoltech, and now he's in Sber devices. So he made like per my request, like 3 years ago, he made this example with music using digital component, but the same code can be used with 3 other components. We just need to connect them and hook up them properly. So let's run it for, let's run the second example, which is example 24, and you can see the music. So like today, like I will just help like each individual to connect components to various boards so that we can create examples. I mean the demo for each board. Okay, it's still running synthesis. This component is already integrated on most of Altera boards, and if it does not, then I will guide you how to hook up pins to different module ports. Okay. Yeah, so you can hear from here, but you can hear this sound is not like a high volume sound. However, if we connect pins to a different component, so let's actually connect different components, and you can hear this will be audible in the room. So let me put a different component to the same pins. So we have to disconnect pins from here. So power. Okay, so we need to look to Digilent. So it's a Digilent PMod AMP3 component. Okay, and pin 1, so let me just quickly connect it to different pins. So here is the pin 1. Okay, pin 1. Then pin 2 is, oh no, pin 1 is selector. So LRCLK. This is pin 1. Okay. Pin 2 is data. So I have a green wire data. So when you connect something, it's better to have color coded. So usually I use red for VCC and black for the ground, green for data, yellow for selector, and then blue for main clock, and magenta for derived clock. Okay, so let's connect. So pin 3 is not connected. Pin 4 is BCK. So BCK is a magenta clock. Wait a second. Think it's okay. Let's see our connections in. Let's see our connections on this board. So this board is the A-links, and if you go inside the wrapper, we can see that MCK is connected to GPIO 12, and GPIO 12 corresponds to pin R3. So then we look to this board, and you can see that R3, so we have P3 and then we have R3. So P3 is 10, and then we have R3, right? Yeah, so 12 is P3 and R3 is this one. Okay, that's okay. And okay, so then pin 5 and 6 are ground in VCC. So pin 5 is the ground. And pin 6 is VCC. So we connected our component in this way. And then some of these components are not using main clock, but this particular component is using main clock. And this main clock is located in pin 9. So then we have pin 7, 8 not connected, and then finally pin 9 is connected. So we need to put 7 not connected, 8 is not connected, and pin 9 is connected. So you connect here main clock. Okay, so let's see whether it works. I may confuse two clocks, and I hope it will not cause short circuiting this board. I had a problem with short circuiting another component. Okay, now let's go back here and let's configure the board again. Yeah, so now you can listen. This is very loud music now. So if you put it into ears, if you put this music into ears, in this case, you can really damage your ear. So for this reason, we don't like to use this component during seminars, because no matter what you tell to the students, they will put into their ears, and like school can be like liable for this. So for this reason, I propose to switch to this component that produce relatively. So for this reason, I propose to switch to these components that produce relatively low volume sound. So now let me just go and replicate this with every person in the room using different FPGA boards. Now let's see what FPGA boards support. Wait, I think somebody turn somebody turn on volume. Okay. Okay. So now yes, I can hear echo. I need to probably put. Yeah, okay. It was yours. Okay. So now like I will go through the room and we create a demo. But before we do this, let's see which components like which board wrappers already support this sound output interface. So I have D215 board. So let's look inside this board wrapper. So in this board wrapper, in this board wrapper we have audio output at the end, and we can see which pins are assigned here just by looking to GPIO and to header like JP5 pin 38. So we need to look to this PNG file and just see where those pins are located. So we can connect uh, jumpers to appropriate pins, and we can also look into a QSF file, a file that maps symbolic names to pin names. So now let's get those boards and create various demos. So we can also use board D0 Nano. So I have D0 Nano board and I have D0 board and like several others. So let's see whether D0 wrapper supports audio component. Yes, it does. So we can use D0 board. We can use D0 CV board. So we have also D1 board. Yeah. And the D1 SOC. Yeah, so we can use D1 and D1 SOC, so we can use all these boards. Okay, so let's just go like around the room and just work with this board. So if people are watching online, we are probably not going to do much online now, and just work with the boards in this room. Yeah. Okay. All right. So this will go. Yes, this has a power here. So do you have a power? Okay, yes. Okay, let's see. So what is the voltage? First of all, you need to find out exactly what is the voltage. What is the current? Because they all have different. There is no standard voltage. But did you check that you got exactly this powers? No, but you got exactly the same power as the private key. I think it's almost actually. This is the largest one. First of all, you got this one. Okay. So did you? Oh, wait, but you said that you lost the power. Oh, well, but you have it at home. You can work with different boards. I do have, but I have power supply for other boards. So this is D1 SoC. So let's check power supply. No, we need to go to Terasic and find Terasic D1 SoC power supply. Yeah, so it's a 12 volt. It's not 5 volt. Yeah, so this can be used for D1, D2, 115, D270, C5G. Yeah, so I do have D2 115. So this is 12 volt to 2 amperes. Okay, so here is the power supply. Okay, this is 12 volt to 2 amperes. So this one. Okay, so what you should do? Is let me show you the process. So what you should do is that you need to go to repository and you need to go to D1 SoC and inside D1 SoC you need to go to the end where you have here microphone, but you don't have that component, which is interesting. So you have only microphone, yeah. But okay, let's see to D2 115. So do we have it here? Yeah, but for G2 115 you do have it here. So what you can do is that right now you can use D2 115 and then for your own exercise you can move code from D2 115 to D1. So you can actually contribute to the board support by putting this code to D1 SoC. Yeah. So first get D2 and then try to connect with but please don't turn on board before you show me what you're doing because it's easy to burn the pins. So I need to check how you connected it. And once you connect and once it works on D2 115, then you do same thing on D1 SoC. So what you need to do is that you need to you can copy and paste this thing, but you need to change pins because pins on D2 115 and D1 SoC do not correspond to each other. So you need to see this GPIO 33 pin, and then you need to go to QSF file, and you need to find this pin in QSF file. So which is GPIO. So again, this was GPIO 33, right? So GPIO 33. Here is a GPIO 33. This GPIO 33 is a pin AH26. Then you need to get a yeah, this is a pin on FPGA. This is pin on FPGA. Then you are getting this picture from here, which is picture from the board manual. So you are getting pin AH26, and you're going here AH26. So where is AH26? Yeah, here's a, so you can see that this is GPIO 33, which is AH26. So this pin. And so you put your, connector to this pin, and then you put connector for 3 volts to this pin and ground to this pin. And then you show me how you connected it. Like I check it visually, and then we put earbuds and we listen how it works. And then you are doing the same thing with the D1 SoC board. This is actually a good exercise. So let's do this during today, and we should be in good shape because we have enough time to do this. Yeah, let me give you first D2 115, and so do like anything you want with it, but please show me how you connect it before you power it on. Okay, yeah, let me give you that board. Oh, yeah. Okay. Next. Okay, so you're using sailing boards. Yeah, so yeah, same power supply, right? Same 5 volt, right? Same 5 volt. Yes, yes, the same. So voltage is the same. Yeah, but you need to connect this to this one has 2 leads, right? Yeah. So let's see which one. So this one for USB plus, and this one is for something else. Connect it here. Yeah, so first try this simple example whether it works. Now with the Salinx, let me see whether Salinx has already this output connected. So if Salinx has already output connected, so let's see. So we have D and we have Salinx. So we have Salinx PMod microphone, Salinx. Okay, so Salinx board specific top. Yes, it does have sound output. So what you do is you look to board specific top, and you can see GPIO 0 pin, so which is J1 pin 24. So GPIO 0, which is 12. So then you go here. GPIO 012. So this is a pin called pin R3. Yeah, this is called pin R3. So here there is some number, but I think this number is a mistake. It's probably number from another board specific top. Yeah. Okay. So looks like you have support this board. So first of all, you should enjoy first of all you need another wire to connect to this board. But so like I would advise to first connect this wire and after this connect. But now we just need to connect jumpers to the pins. Yeah, this is actually yours. Yeah, mine. Yeah, this is fine. So you have the same board. Yeah. Okay, this is fine. So now what you do is that you get jumpers. Yeah. you figure out from board wrapper where is connect those jumpers. So you have names for the pins here, so you can see like R12, the P. So generally pins are here, right? And you can find those pins on a board specific wrapper, right? And once you connect all wires, so like I would recommend to put black to ground and red to VCC, and so you can connect with the different colors, and then like I will give you one of these components. So you can use these components and the clear parts. So this, like usually this is something clear part from there. You usually have single lists with clear parts, which has two outlets, which is very convenient. Yeah, so you can use this here but and you can use this component. Yeah, and you can just check whether it works. And then you can also connect microphone. So you also connect microphone. Okay, so you are working on connecting output. You are working on connecting this one. The rest of it. Okay. Okay, now you. So окей, хорошо, да. Так чем вы занимаетесь без какого рода проекта? Нет, но вообще раньше. То есть это значит гитары делали, а еще что? То есть в какой степени используют кирпичей? Фильм у меня было такое, везде SystemVeriog что такое? Я потом для начала апдейтить, просто считать гонял, чисто на Ну, для большого проекта это такое бывает. Если нет, ну, если вы хотите просто, так сказать, начать перевод с некоторой базы, то вы просто можете начать вот с первого примера и пройти сразу туда несколько примеров. Вот, и да, допустим, его весь правда, это старая, сейчас новая. Так, сейчас я возьму другую. Окей, значит, Шурик, а ты можешь на самом деле, вместо того, чтобы это делать, ты можешь сам сесть вот с товарищем, мы, значит, показать, как запускать примеры. Сейчас я тебе дам... можно же с этой же платой это и сделать, да. Берешь эту плату, да. Короче, вы просто взять вот эту плату. Вот, и потом можете вдвоем подсоединить дальше. Вот это не шло. Вот, значит, это можно запускать либо с того ноутбука, либо вы можете запустить с внешнего загружаемого SSD. Если SSD, который вы будете на своем компьютере, там потом находится Linux, и там все. Я могу выделить SSD для этих целей. Сейчас перегружу. Все, короче, конечно, лучше. Так, ты хочешь к этому присоединиться? Интересно, конечно. Okay. Okay, so you know what to do? Not really. I'm a little confused. Okay. Yeah, but this guy here, the confusion is a part. Yeah. First, you're using the first three things in this row, which is GPU 3, yeah. Right. But actually, this is JP5. From here, you're using all these wires. You're using 3 here and 3 here. Yeah. So you can see 2, 4, 5, and then 1, 3. So 1, 3 is a ground. So like I'm using 1, 3. Wait. So 0. So like 0, 1, 2, 3. So like I'm using all of them. I'm using 6 wires at the top. Yeah, GPU, it's on the left side. So you see the 3 wires on the right side, 3 wires on the left side. But how come you don't have it like over? Yes, I do have here. GPU 1, GPU, so this is, so 0. Yes, I'm using 0, 2, 4, 5, so 1, 3. So here is GPU 0, so 0 is this one. Yeah, left. Yeah, why do you use right over here? Because here, this is a good question. This is just moved from another code. That's not right. Okay. So you're using things 0, 2, 4, 5. Oh wait, are you looking to D2 115, right? Okay. So which means that this is incorrect code. This is D2. Wait. No. There might be something else. now let's look into that one. Let's look into QSF file. So now look to QSF file and find the GPU ones. No, this is PNG file. So go to QSF file. So go to port specific QSF file. QSF is a file which provides mapping between symbolic names and actual FPGA pins. So now let's go there. Huh? They do it because the manufacturer of FPGA has no idea about the port. They just have. No, he doesn't. He has no idea. He knows only about pins which coming from the chip. So he needs to connect those pins coming from chip to GPU. So now go down here and find for GPU 0. So GPU, yeah, so find for GPU. Just find it. Just look for GPU with a capital. Yeah, so you can see here that actually, well, they have different. So they have names like D25. I think that code in the file is a mistake. Which one? No, in a wrapper one. Oh, but actually, let's scroll down. Yeah, I mean, a comment in very local file is not. So let's go back to the comment. Oh, what? This is not D2 150. This no. This is called D2 150. It's different. D2 and D2 150 is different. So it's different boards. But now let's go to 215. Maybe they put cycle. The other one says side. No, cycle. No, this is a D1 SOC to distinguish it from D1 port. Because D1 is different. Okay. Those boards have some. Okay, now let's look here to QSF file. Okay. Now let's call for GPIO. Okay. So this here, so looks like that Verilog file just person mechanically moved. The person who was putting that wrapper just mechanically put command from another file. So let's go back to that file. I probably need to remove that command because it's incorrect. So what you need to do is that you need to yeah, you go to Verilog file. You go to Verilog file. Yeah. So now what you need to do is that you need to so these comments referring to the map. Those comments simply wrong. Just that's what they should. Just ignore them. But the purpose is to talk about this back. Yeah, purpose is to put here names from like QSF file, but like apparently it is simply wrong. So like apparently you just need to use GPU here and GPU on this picture. So comments usually ignore. Yeah. So this is a GPU. So you look to this picture and you see how you like it uses GPU 0, 1, 2, 3. Why use it? But this one uses 31, 33, 31, 27, 29. Let's go down. think that once you connect them, they will be continuous group. Once you connect them, they will be continuous group. Yeah, they are continuous there, but the problem is that this output matches sequence of pins on this component. So if you get this, so like if you get this component, I mean no, not this one. One second, where is that component? Allowed one. Yeah. So if you get this allowed component, if you get this allowed component, you can. If you connect these pins, they will connect in same sequences on the board, but in the code they are different sequences because in the code the sequence is different than those pins. But you can try first.
Why don't talk disconnected yet? Oh, it's because they've got this board. You want to use a pair of 4 and 2. That's why. And you want to have a gap between them.
So first of all, this red is a power and this one is a ground. So they are connected to dedicated power and ground.
See, that's not in the Verilog file.
Yeah, so they're not in Verilog files.
Okay.
So in Verilog files there are those 4 pins.
Okay, and they should be consecutive PIO pins, right?
They are, yes, you can see that here they are consecutive and here they are consecutive, but in the code they are in different order.
Because this is in a different order?
Yeah, because this is a different order. So code and pins here. So here they're more of chaotic, but in the code they're in some logical sequence.
You can make the 4 here, map to the 4 there. You don't have to.
So here, if you
because
look
then you're mapping
here,
you're
so
wrapping it in software and then you're wrapping it in hardware. It's two calculations.
the problem is that sequence here and sequence in the code, they are a little bit different because in code they are in logical way. So master clock, block clock, selector, data. But here they are in different order. So first you get selector, then data, then block clock, and then master clock. See? So like basically here they insert in logical order, but in the but on the header for this component they are in different order. Yeah. So basically we try to put order here in a way to simplify connection for the user, because user do not see this. User do not see this code. No, you are in this case you're not user. You're a person who is adapting to the new board. Yeah, but user just see pictures that connect these pins to these pins. So here pins are in consecutive way, but this consecutive way does not match order in code. Code we put in logical way, because in code you want to put clock first and data,
so I need to look at that
second.
file. Which file is that?
Huh?
Which file is that?
This is board specific tool. You're looking.
The one I'm looking at?
Yeah.
Oh, okay. That's the one that's got the wrong
comments
here.
So this comment I should remove this code. So let me add.
That's not a problem.
Yeah. So just look to pin indexes and connect according to pin index. Yeah. So this is a component. Let me give you pins. Yeah. Those are jumpers. Yeah. Just connect with those jumpers. Yeah.
And I need the definition of pins which are on here.
Yeah. So you can see that. So you can see that this ACK is actually M clock. So this is master clock. Just it was called master clock in another component, but on this component it's called something else.
This is the GPIOs.
Yeah, this is a GPIO. GPIO.
That's your board.
Yeah, but
I need
so this is a GPIO, but you need to look to the names of a logical signal in this component. And
I don't need to do a map. I just need to look at the names.
Yeah, you just need to look to the name. So this name is like master clock, and this is block clock, which is and block clock.
What does that mean, block clock?
I am not sure. This is for the protocol. I believe this is a clock used to sample data.
Logical clock.
Yeah,
Serial clock.
I think that that B clock is a serial clock, but M clock is some reference clock which is not used by some components. So let's see what is here. So here we have SCK, which is same as SM clock, and we have a BCK, which is probably corresponds to B clock, and then we have a D in, which is data in, so serial data, and then we have LCK. LCK is a left or right. LCK. So here it's called LCK, but actually this is left right CK. And then we have ground and we have power. So and we need to put ground and power to a dedicated ground and power pins. So let's look here to yeah. So we just connect them to those pins. So just like connect if you make mistakes. So let's do this. So do you try to connect?
I need first get to the electrical I need to go to the electrical use now. So I don't know.
Is it yours or mine? This is yours. This one. Okay. Let's see. So first of all, you should you should open a repository, a different one. So you need to open. So you can. You need to open this repository basics regarding the music. Yeah, and now you need to go. So you are going here. You open basic graphics. Now you are going to. So now you're going to boards, and you are going to this APIX board. Oh no, sorry, you're going to save it boards. You're going to save it. Yeah, this one. So now you're looking to board specific topic. Right. And in board specific topic, you need to find pins. Okay, you need to find this pin. So pin 12. 12, 10, 16. Then you are going to QSF, and in QSF, you're going to GPIO this 12, 10, 6, and say mapped to pin L9, so pin R3, pin P3. So now you are using those names. You found those names here. And then you put your jumper connectors to this pin. So what I recommend you to do, I recommend to get a piece of paper. Yes. And on this paper, you just write GPIO name and then write pin names and then put it here. And then also use color code. So to put this is for VCC and this is for ground and connect this. Ой, так, сейчас. Прежде всего, у вас тут Windows или что? Все, это у вас демо, все, я все понял. Значит, так. Я знаю эту проблему. Значит, эта проблема заключается вот что. Вам нужно пройти в BIOS Center. Это именно чисто деловская фигня. Тут нужно поставить другой пас. Сейчас. Значит, тут нужно пас, он так, сейчас.
здесь мы уже переставили. И эксперимент можно сделать еще нужно, если отключить через это, потому что тут нужно поставить, к сожалению, пас, нужно сделать этот option, и вот в этом option нужно поставить файл. Проблема с этим файлом, этот файл не знаю, если он скажет, что, по-моему, нужно ставить что-то вот это вот не файл, а вот по-моему, нужно ставить и может ставить это тоже. Или ставить грамм, вот. Попробуем поставить например. Я, к сожалению, не знаю, он точно знает. Если это назвать, назовем это какой-нибудь UPC. Теперь его, теперь можно убрать это, можно посмотреть, что да, и теперь нужно apply. Не видим, что это правильно файл. Ладно, сейчас я еще можно попробовать заводить Legacy мод, если есть поддержка Legacy. Вот так. Да, грубо. Да, что это граф 64.
Он сейчас на этот диск записал development class, да?
Он FIOS, добавил FIOS. Что оно грузится с этого. Но потом там нужно вернуть обратно вот это самое. Вот это. Да, ну пойдем так, слушай, давай. You're right.
Хотя она, конечно, там не только пауза, там
с собой нет, только что работает. Вот. Это тоже это видео. Champagne.
Like many people today, because we are doing something like relatively poorly, so just okay. So yeah, what are you doing generally? So what how do you use it?
I use it in 2 years.
So but did you do the basic side or so which
This was a small consulting company for and everything except for I did do testability, I did do place routing. So in terms of your, if
refresher. So are you trying to learn these features of SystemVeriog, or like are you trying to so what's the order where like to me?
Just using Verilog. So not system Verilog, this is not system C.
Very well identified.
I'm not sure.
So there was a Verilog 95, Verilog 2001, and after this system.
Okay. No, that's fine.
Okay, and so what type of microarchitecture do you do? So it wasn't like CPU cores or like networking or multimedia or whatever.
This is audio. Yeah. But
Audio.
it has some very basic graphics.
Very basic. Yeah, actually today we are connected microphones, so we are doing some like I2S interfaces a little bit. Yeah. Yeah. So, but what you can do if you want to like do refreshing SystemVeriog. So what the method which I would recommend is to like at the same time study standard is do like bunch of exercises. And basically I have a set of exercises which you can try. Then just to see how it works for you. And those like exercises start with something very primitive, like to do like multiplex or 5 ways, depending. But then they proceed to something more interesting. So with like pipelines and with flow control, with like FIFOs and creating counters and all those things which you use. So what I can do is that I have a bootable disk. Actually, you can start a refresher from just running this simulation with those exercises, and I can see how far you can go. And that's it. So let me get such disk. So you have booted. So now you just exit somewhere. Yeah, so you can use your laptop or you can use another one. So what the
Does that boot into that system?
yeah, you can boot everything from the disk. Then like you can actually do this at home as well. So do you want to try to put this from this disk to your system? If you are not sure, you can just use
Okay,
laptop.
okay, sure.
So like it's up to you.
Okay, maybe another.
So do you want to use the laptop? Let's use actually this one if you don't mind small screen. If you don't mind. You can get the light. Okay, so let this be short. You're fine with this.
Sure, I'll be okay.
So this uses Ubuntu. So and so basically. So basically, repository. You can actually do this on your system just by getting a repository called SystemVeriog home. Okay, this is from GitHub. And
What about simulation? That's great.
So let me show you. You're using Icarus. So here to check, we use Icarus Verilog. So Icarus Verilog is a free but slow simulator. So it's called the Icarus Verilog. Icarus Verilog. So this is in here in so let's get like a combination of each. So here is the first exercise. So first you get like a multiplexer is selector is 2 inputs. This is example, and then the first question that you here is multiplexer for two inputs, and make a multiplexer for four inputs using like ternary multiplication. Okay, so this is like so you just start from such simple exercises, and then once you do exercise, you run this shell script, which is writing Icarus way, which is very simple. So then like it runs a simulator, so you can just you can just run this script, and this so you fail. So now suppose we do the very first exercise. So we have this first exercise, and suppose like you put here some code, and then you run the script, and it will tell you pass. So, because it has a very rudimentary first page. So this simply checks that this is like a trivial test page. So you can start with this first combination, then like finally like around like 0.5 you're going to like interview level questions where you have some pipeline with a 5 and you need to put some, then you go to like some CPU questions, so you get some trivial CPU and you need to put some stalls inside and stuff. But you can start from the very first one, and you can actually get this from a GitHub, like on your system, and you can install it. So you have Windows or Linux. Okay, so what you do in Windows? Let me actually show how you can run it. So yeah, you can just put your laptop, and I will show you how you get it. And by doing this actually shows some features which didn't exist in Verilog 95, like generate, many other those exercises they usually expose where people need a refresher. So you're mostly interested in RTL features and not the verification, but verifications, all the verifications.
I think ideally would like to get a refresher on Verilog and test the installation and move into FPGA.
Yeah. Okay. So now let's start. So you go to GitHub. You find by my name you find the repository. Just go to GitHub. Yeah, I think we stopped recording because we. Yeah, just a second. Yeah. So yeah, some people are coming, so we probably stop. We probably stop recording because I will just individually work with the people. Yeah. So now some like new people came and we want to show examples and refresh and so on. Okay. So thank you.